Greetings one and all. So this is the second video of 3 only for the year 13 version of the binomial expansion. So in the previous video we had a look at how we can expand things in brackets where the leading term is 1 plus something else, all to a power which no longer needs to be positive integer. It can be negative, fractional or both. But what we didn't look at last time is the scenario where the leading coefficient in the bracket is non-unitary. For example, what if we had 5 plus x, or 2 plus x, or even 3 plus 5x, something like this. So what we need to do is adapt what we learnt from lesson 1 to answer those sorts of questions. Before we do that though, obviously there's some warm-up questions which you know by now, so here they are, 4 to try, almost as ever, sometimes there's 3 or 2. Try these on your own, and when you're ready to see the solutions to them, press play, and I'll try and make them make sense to you. Okay, so let's have a look now at question 1 together. So for question 1, what we have here is a circle, C, with equation x squared plus y squared plus 6x minus 4y plus 5 equals 0. Find the coordinates of the centre of C and the exact radius of C. So if you remember your year 12 stuff, to find the equation of a circle, we can partition the x stuff and the y stuff into brackets. Essentially, we complete the square on the x stuff and the y stuff separately. So for part A, x squared plus 6x, we say is x plus 3, because half of 6 is 3, squared, then we always minus off this thing squared. So this is just a rewritten form of y squared minus 4y. So we do the same for y squared minus 4y. So we have y, half of minus 4 is minus 2. We square that, but we minus off minus 2 all squared. So it's always minus something. Minus 2 times minus 2 is positive 4, so we minus off that 4. And of course you have this 5 at the end to deal with in a moment. All that equals 0. So that's all we've done so far. So next we can neaten this up. So we have x plus 3 squared, and we have y minus 2 squared. Now minus 9 minus 4 is minus 13, plus 5 overall is minus 8. So if we add 8 to both sides in a moment, we should see that x plus 3 squared plus y minus 2 squared equals 8. And this is the standard form for the equation of a circle for A level. So we've basically done A. So if we look at the numbers here, it tells us what the centre is. So therefore, the centre is going to be these numbers here with their signs switched. So plus 3 becomes minus 3 for x, and minus 2 becomes plus 2 for y. And B, we've got the radius here as well. The radius is the square root of this number at the end. Another way of saying that is the radius squared is 8. So therefore, the radius will be the square root of 8. We want this in exact form. If you type root 8 into your calculator, you would get 2 root 2. And so that's the answer for the magnitude of the radius in exact form, just as this is the coordinates of the centre. So that's question 1 done. Question 2, a trig identity. Show that 10 cos squared x minus sin x minus 7 all over 2 sin x minus 1 equals, well, is identical, I should say, to minus 3 minus 5 sine x. So here, if we notice, we need to start with identities with one side and manipulate it so that it becomes identical, literally identical to the other side. So I'm going to start here with the left-hand side. LHS for short and to be lazy. Now, if you notice, our target here has nothing to do with cos in it. So we need to eliminate anything to do with cos or cos squared and replace it in terms of sine squared. So what identity relates sine squared and cos squared? You should hopefully recall that sine squared plus cos squared is always the same as 1. So this cos squared x, I can subtract sine squared x on both sides. We can see therefore that cos squared x is going to be 1 minus sine squared x. So the first thing we can do is to change this with 1 minus sine squared x. So when we've got it all in terms of sine, that's a good first step. So over here we're going to have 10 lots of 1 minus sine squared x, because that is cos squared in terms of sine squared, minus sine x minus 7, all over 2 sine x minus 1. So what we need to do here is obviously expand this out and then simplify if needed. Just predicting over here I'll need some more space, so I'm sectioning out the page accordingly. So 10 times 1 obviously is 10. 10 times minus sine squared x is minus 10 sine squared x. Then minus normal sine x minus 7. All of this over 2 sine x minus 1. Now at the top what we have is a very ugly looking quadratic in terms of sine. So what we can do here is simplify this ever so slightly. So I've got minus 10 sine squared x minus sine x, and 10 minus 7 is positive 3. All of that is still over 2 sine x minus 1. So what's that helping us with? Well, what we can do here, a suggestion would be to factorize out the top into a factorized quadratic, hoping the hunch here is that this 2 sine x minus 1 on the bottom should cancel with a 2 sine x minus 1 on top to leave us with this thing here. So the hunch is, when it comes to practice, that the top will factorize. However, factorizing quadratics, we only really ever consider this at GCSE and indeed for A-level, when the coefficient of a quadratic thing is positive. So what we're going to do at the top is I'm going to factorize out a minus 1 to make everything positive on top. So if I factorize out this minus 1, I'd have 10 sine squared x. The minus sine x becomes plus sine x, and the plus 3 becomes minus 3. So I'm just switching the signs of everything essentially. And all of that is going to be still over 2 sine x minus 1. So now, at this stage, we can use the handy ClassWiz calculator to help us sort of hack how to factorize this quadratic. I'll explain why if your teacher's not showing you how to do this. It's very straightforward if not, so don't panic. So, sine squared x and sine x, it's a quadratic in terms of sine x. So in terms of typing this on the calculator, here's what we need to do. So we go to menu, press, or scroll along to option A for equation / func for function, press equals. Now we've got a polynomial, it's a quadratic, so degree 2 in terms of sine x. So our x squared term is sine x all squared. So we've got 10 lots of sine x squared. I'm ignoring this minus 1 outside, you see, plus 1 lot of sine x, and minus 3, press equals and equals again, and these values here tell us what the roots are. So in terms of factorizing it, what we do, if we have a denominator, we just shove this denominator next to the quadratic term. So because this is a quadratic in terms of sine x, we stick this 2 next to sine x. That's the hack. So you do 2 sine x, then the number at the top, you leave exactly as it is, but you switch its sign. So that positive one just becomes a minus 1. Press equals again, and we do the same thing. Any denominator we shove next to sine x. So that 5 we put next to sine x. So we have 5 sine x. In the numerator, we keep exactly as is, but just switch the sign. So this minus 3 becomes plus 3. Again, all over 2 sine x minus 1. Now what you should spot is, indeed, there is a cancellation we can do. We can cancel the 2 sine x minus 1 at the bottom with a 2 sine x minus 1 on the top. So now we're nearly home and dry. So now we've got minus 1 lots of 5 sine x plus 3. Finally, we can expand this. Minus 1 times positive 3 is minus 3. And minus 1 times 5 sine x gives us minus 5 sine x, which you can now see is exactly the same as the right hand side. So that concludes our proof of this being an identity. We've got the left step by step to equal the right. Question 3. We have a function f of x equals x cubed plus 3 lots of bx squared minus 30x plus 9. We're told that x minus 3 is a factor, and therefore to find the value of a constant b. This essentially is the factor theorem. If x minus 3 is a factor, then this implies, and this is the same as saying, that f of this number here switched with its sign, so f of positive 3, get my words out, will equal 0. So if x minus 3 is a factor, f of positive 3 will equal 0. Another way of thinking about this is, if x minus 3 is a factor, then 3 is a root. So f of 3 will equal 0. So all we need to do here is sub in where x is 3, and then b will drop out accordingly. So we're just going to sub in that x is equal to 3 and set it equal to 0. So next step, 3 cubed plus 3b times x squared, so 3b times 3 squared, minus 30 times by 3 plus 9, that is f of 3, that all equals 0. And like I've said, all I'm doing here is just subbing in that x is the same as 3. So let's just evaluate what we can. So 3 cubed is 27, 3 squared is 9, so 3 times 9 gives another 27, therefore 27b. 30 times 3 is 90, so it's going to be minus 90. Then the plus 9 equal to 0. So we've got 27 plus 9 minus 90. This is probably safer being done on a calculator, because you've got a calculator, so why not use it? 27 plus 9 minus 90 should give you minus 54. Yes. So this simplifies to 27b minus 54 equals 0. Add 54 onto both sides. 27b equals 54. Oops, what happened there? So therefore b will be 54 over 27, which gives us a value of exactly 2. So b would have to be 2. Finally, warm up 4. We have a function f defined as f of x is 10x all over 2x plus 5, where x is any real number so long as x is at least 0. First, we need to find the range of f. So what I'd suggest for part A, it's suggested, you don't have to, but I strongly suggest doing a sketch of this curve. So it starts when x is 0. So if we imagine x going along and y going up, let's just think what would happen if x is 0. So f of 0, 10 times 0 is 0, all divided by nothing plus 5. 0 divided by 5, f of 0 is 0. So it's going to start from the origin. Now, because you've got this function here, which is fractional with a variable on the bottom, just be careful and be on the lookout for asymptotes. So be thinking, what happens, or what will happen when x goes very, very big? So as x approaches infinity, then 10x over 2x plus 5, as x gets absolutely huge, this 5 becomes obsolete. This 5 is nothing compared to the massive size of 10x and 2x. So this will become pretty much the same thing as 10x over 2x. The x's cancel, so it's going to go towards 5. The only thing is it going to go towards 5 from below or 5 from above? Well, it's starting from 0, 0, so it's going to approach 5 from below. But another way you can prove this to yourself is as follows, and I like this method quite a lot if I do say so myself. Just try on your calculator x being something really, really big. So what I'm going to do here is I'm going to try x being, let's go for 1,000,000, because 1,000,000 is pretty big. Hope you agree. So 10x would be 10 times 1,000,000, like so, all over, that didn't quite work, did it? I'll toggle back and put that as 10 times 1,000,000. 10x, 10 times 1,000,000, all over 2 lots of x, 2 times 1,000,000, then plus 5. You get 4.999, so it's getting really, really close to 5, but we'll never ever touch. So what we're saying here is, as x goes towards infinity, f of x will approach 5 from below. So we can say 5 minus, which is essentially just a way of writing. This is notation to say 5 from below. So the curve would be something like this. It gets closer and closer and close to this dotted line, but it's never allowed to quite touch it. And this is the line where y is equal to 5. So you're probably thinking, well, how do you answer the damn question then? Well, I'm getting to that. The range of f just means the values that f of x is allowed to take. So the smallest value that f of x could be is it could be 0. So f of x is at least 0. And the maximum limit is 5, but never will quite touch 5. It will approach 5, but never quite touches. So therefore f of x is always going to be slightly less than 5. And if it's less than a tiny, tiny, undefinable amount. So that's the range of f of x. Finally, b is slightly harder, but not as hard as what you might think. Finding the inverse function. This doesn't mean literally do the reciprocal, it means the inverse. This again is notation. So for b, the method we can use here is to change x into the subject, and then finally switch the x and y's around. So I'm going to call f of x as y. So f of x, I'm going to think of as being y. So think of it in being y equals 10x all over 2x plus 5. So let's get x as the subject. So let's multiply through by 2x plus 5 on both sides. So multiply both sides by 2x plus 5 on that side and on the left-hand side. What we'd get as a next step will be y brackets 2x plus 5 equals 10x. Now expand the brackets. So y times 2x is 2xy. Y times 5 is 5y. And then 10x is obviously just 10x. Now what we need is all of the x's on one side. So what I'm going to do here is subtract 2xy from both sides. So 5y is 10x minus 2xy. Next, we can factorize out an x here. So we have 5y equals x, 10 minus 2y. So therefore we'd have that x equals 5y over 10 minus 2y. The final thing we do is we replace y as x. So what we say finally is, so f minus 1 of x equals 5x, we call it now, all over 10 minus 2x. And then we're finally done with a warm-up. So what we can do now is have a look at the main body of the lesson, how to do the binomial expansion when the leading coefficient is not a unit. So let's have a look and consider this next. So expanding a plus bx to the power n. So how would this be done? Well, the binomial expansion of a plus bx to the n can be performed by manipulating this bracket here algebraically so that the leading term in the expansion is yet again 1 rather than a. So all we need to do here is actually fairly simple. We just have to factorise out the a before we expand to the power n. So it's just something along these lines. So we have a plus bx to the n. Factorise out the a. So we have a brackets 1 plus ba over x. All of that is the same as a plus bx. So we do all of this thing to the power n. Then to do a, then these in brackets to the power n, we do a to the power n first, then these brackets to the power n next separately. So what does this mean in terms of actually performing the binomial expansion? Well, it's not too arduous. It's nowhere near as hard as you may think, as long as you're careful, of course. So what I'm saying here is, thus, if you expand a plus bx to the power n, it's just done by finding the series expansion of 1 plus b over a over x to the power n, this thing here, and then after, just multiply everything through by a to the power n. The number what you had initially at the front of the bracket to the power of what you're raising the bracket to. So, as ever, saying it in words is never as easy as understanding it as it is by just doing it. So let's have a look at a couple of worked examples just to make this as clear as can be. So worked example 1. Part A, find the first 4 terms of a binomial expansion of 1 over 2 plus 3x all squared. Then part B, state range of validity is all it's saying. So let's just do part A obviously first. So for part A, what we've got here is 1 over something. It's 1 over, in particular, 2 plus 3x squared. In algebra, if you got something where it's 1 over, you think this is a reciprocal. So this is the same as saying it's 2 plus 3x to the power minus 2, because this bracket's on the denominator, so this is the same as the denominator to this power made minus. But like I just said, what we need to do is factorise out this lead coefficient here. We need to factorise out the 2 before we can proceed. So what we're going to do here, first of all, in nice big squared brackets, I'm just going to rewrite this here in these normal brackets as 2 lots of 1 plus 3 over 2x. If you're not sure by that, just convince yourself by expanding this out. 2 times 1 is 2, check. 2 times 3 over 2 is 3. So it does work. So it's all of that to the power minus 2. Next, if we're doing a list of things to a certain power, if we're doing a product to the power of minus 2, it's the same as this thing to the power minus 2, multiplied by this thing to the power minus 2. So the next step is to realise that this is the same as 2 to the power minus 2 times 1 plus 3 over 2x to the power minus 2. Now 2 to the power minus 2 is a quarter. So now what we do is just say this is all the same as a quarter of this binomial expansion. So now what we do is we can perform the binomial expansion on this thing here. Now I'm not going to put the formula up like I did last time. I'm just going to talk you through how we do it. So for the general binomial expansion, the first term is always the 1, assuming we've manipulated into the form where the first thing is a 1. So it's 1 plus the power multiplied by this term here. So next it's minus 2 times 3 over 2x. So 1 plus minus 2 lots of 3 over 2x. We need to do the first 4 terms. So these are the first 2 terms. Next, we take the power again, take 1 off it, so minus 2 times minus 3. This is 2 numbers, so I write 2 factorial. And because this is 2 values, I now do this n term here squared. So it's 3 over 2x all squared. The final one we need to consider, because we only need the first 4 terms, is, again, we take the power, minus 2, take 1 from it, minus 3, take another 1 from that, get minus 4. This is 3 numbers, so I divide by 3 factorial. And again, because there's 3 numbers on the top, I multiply all this by this thing here, all cubed. So it's going to be 3 over 2x cubed. Now obviously this would carry on, but we're truncating to the first 4 terms. So the rest here is going to be more or less negligible. So let's just neaten up what we have on the inside of these big squared brackets. So all I've done here is all of this thing here in green is this big squared bracket here. So that's all I've done. I've rewrote it like so. So I've got a quarter of, well, the first thing, 1 is just 1, obviously, that's easy. Minus 2 times 3 over 2. Let's just check that out. Why not? I mean, it's fairly easy. You don't need a calculator to do it, but just to be safe, minus 2 times 3 over 2. That's going to give us minus 3. So we have minus 3x's. This next thing here, let's do this a bit more carefully. So I've got minus 2 times minus 3 all over 2 factorial. So press shift in the reciprocal button here. I'm going to multiply this by 3 over 2. I'm going to be lazy and think of 3 over 2 as 1.5, which it is. I can type in 1.5 squared, and that'll tell us the coefficient of the x squared term. 27 over 4. So we've got plus 27 over 4x squared. And the final one in this expansion is this here. So minus 2 times minus 3 times another minus 4. So I'm just going to edit what I've got here already. This time divide by 3 factorial, not 2 factorial. So edit that 2 to a 3. The power now is cubed, so I'm going to edit the 2 to a 3. Press equals, we get minus 27 over 2. So it's going to be minus 27 over 2 x cubed. Finally, we just take all of this and multiply everything here by a quarter. In other words, we divide all of these things here by 4. So 1 divided by 4 is a quarter. 3x is divided by 4 is 3/4 of an x. So I have minus 3x over 4. Or minus 3/4 of an x, whichever way you want to think about it. 27 over 4 divided by 4 is going to give 27 over 16. So I have 27x squared over 16. And last but not least, 27 halves divided by 4 gives me 27 eighths. Try the calculator if you want to. I would recommend that if you're not sure. You should get 27x cubed all over 8. Finally, part B, it asks us the range of values of x for which this is valid. So look at the expansion we did here. The expansion was this thing here. So what we need for part B is we need the size of 3 over 2x to be less than 1. So in other words, that's going to be less than 1 when x is less than, the size of x is less than 2/3. So in terms of a range, we can put this here, that's absolutely fine, or we could say x is greater than minus 2/3, but less than positive 2/3. If we substitute in x between these two values here, we get that 1.5 times anything between these two is indeed with a magnitude of less than 1. So that's worked example 1 done. We'll do one more, then it's over to you lot to try some of these independently. Worked example 2 is something of a beast. It comes in 2 different parts. We need to show that the first 3 terms in ascending powers of x of this binomial expansion here, 3 over 3 minus 2x plus 5 over 2 plus 3x, are 7 over 2 minus 37x over 12 plus 437x squared over 72. So that's quite a mouthful, quite an awkward expansion to do. So all we do here is we take each part separately. So first of all, let's think about the 3 over 3 minus 2x. Next, we'll think about the 5 over 2 plus 3x as well. So first of all, just think about this one here. So what we need to do here is think about how we can partition this out. So for part A, what we have is 3 lots of 3 minus 2x to the power minus 1 essentially, because this 3 minus 2x is on the bottom of a fraction. So we can rewrite this as 3 times by 3 minus 2x to the power minus 1. Now, we can therefore now leave this 3 on its own on the outside. That's not what I wanted. Sorry, everybody. That's more like it. So what I can do here, leave that 3 alone, and now I'm going to factorise out this 3 from inside the bracket. So I can say this is 3, and then this 3 minus 2x here, I can factorise out the leading 3 from it and say it's 3 lots of 1 minus 2/3 of an x, where all of that is going to be raised to the power minus 1. So I'm just going to do the binomial expansion on this thing here first, and then what we're going to do is multiply it all by this 3. So first of all, I've got 3 times by 3 to the minus 1, because I do this power minus 1 to all these things on the inside. So it's 3 times 3 to the minus 1 times by 1 minus 2x over 3 to the power minus 1. Now 3 times the reciprocal of 3, luckily for us, makes it much neater. That'll just simplify just to 1. So it's going to be 1 lot of this following expansion, which makes it much nicer. So the first term of a binomial expansion is always going to be just 1, when the leading coefficient is 1, like it is here. So we've got 1, then we're going to do plus this power here, multiplied by minus 2x over 3. Now we need to go up to the x squared term, so we just need 1 more. So we do minus 1. Minus 1 taken up 1 is minus 2. Those are 2 numbers, so divide by 2 factorial, then multiply by minus 2x over 3 all squared. So because I'm multiplying by 1, I can just say that all this is just what's inside the bracket. So I'm going to have here just 1. Minus 1 times minus 2/3 gives me positive 2/3, so I've got plus 2/3 of an x. And then, this one here, minus 1 times minus 2 is positive 2, divided by 2 factorial gives us 1. Check on a calculator if you're not sure. And then minus 2/3 times another minus 2/3 gives us 4/9. So this becomes just 4/9 of an x squared. So that's what this one becomes. Now we consider what 5 over 2 plus 3x is, in much the same way. So we need to think of this as being 5 lots of this to the power minus 1, because it's on the bottom, it's the denominator. So next, we leave that 5 as is, and we need to factorise out this leading 2. So if I take this 2 out of 2 plus 3x, it becomes 2, then brackets 1 plus 3 over 2x, or 3x over 2, whichever you want to use. I'm going to go for 3x over 2 in this case. But all of that is to the power of minus 1. So then I've got this 5, then 2 gets raised to the power minus 1, as does this bracket, which I can now perform the binomial expansion on. So it's 1 plus 3x over 2, all to the power minus 1. So this thing here, 5 times 2 to the minus 1, if in doubt, just calculate it. So 5 multiplied by 2 to the power of minus 1, that just gives 5 over 2. So it's going to be 5 over 2 multiplied by this whole expansion here. So first of all, 1, the first term is just going to be 1, plus this power here multiplied by this term, so it's going to be minus 1 times 3x over 2. And the next term, minus 1, minus another 1, minus 2, all over 2 factorial, divided by 3x over 2, all squared. So that's going to give us 5 over 2. If we now neaten all this up, so 1 just stays as 1. Minus 1 times 3x over 2 gives minus 3x over 2. Minus 1 times minus 2 is positive 2. And then we do 2 factorial divided by that, so then we're going to... So all this becomes 1. Minus 1 times minus 2 is 2, divided by 2 is 1. Then 3x over 2 all squared gives 9x squared all over 4. Then finally expand all this, multiply it by 5 over 2. 1 times 5 over 2 is 5 over 2. 5 over 2 times minus 3 over 2, we can do this on the calculator if we need. So 5 over 2 times minus 3 over 2, that gives us minus 15 over 4. So we have minus 15x over 4. And finally, 9x squared over 4 multiplied by 5 over 2, that's going to give us 45x squared over 8. So we've got the two ingredients. We've got this fraction here written as a binomial expansion, and this one in blue written as a binomial expansion. The final thing for part A is now to combine these two and show that these two combined equal this result here, which we need to prove. So that's what we're going to do here next. And this step is actually fairly straightforward because we have all the ingredients here, all the raw ingredients in front of us. We've got the constant terms, combination of 1 and 5 over 2, the x terms, combination of 2/3 and minus 15 over 4, and the x squared terms, which are a combination of 4/9 x squared and 45 over 8 x squared. So the next step is actually, relatively speaking, fairly simple. So what we can say here is, therefore, f of x is approximately, we've got 1 plus 5 over 2. So that's the constant term. We then have 2/3 of an x minus 15x over 4. And finally, the x squared terms, we have 4/9 of an x squared plus 45 over 8 x squared. So the calculator can work out these fractions for us, which is obviously very convenient. This one, I don't think really you need to do this with a calculator. I mean, you can if you want to. 1 plus 5 over 2, 2 halves plus 5 halves gives you 7 halves. This one here, 2/3 minus 15 over 4, what does that give us? Well, again, this is where the calculator comes into play. So what we do here is just do 2/3 minus 15 over 4, and then we can just see what the result is. So if I get this here and make it a tad bigger, so we're going to get 2/3 minus 15 over 4. That indeed does give us minus 37 over 12. So we have minus 37 over 12x, like we needed. And finally, just to double check, 4/9 plus 45 over 8 will, or I hope, it's made a terrible blunder, will give us 437 over 72. And indeed it does. And that's proven what we want to prove. That's exactly what we wanted to show. We've shown that this here is exactly what's dropped out when we apply this binomial expansion, truncated to the first three terms. Part B, we need to state the range of values of x for which the above expansion of f of x is valid. So what we do here is we need to have the size, the magnitude of the thing after the 1 in these brackets to be less than 1 in both cases. So for B, what we need is to consider what we did the binomial expansion on. So even though we did the binomial expansion for 3 over 3 minus 2x, the binomial expansion we actually did was only based off the 1 minus 2/3 x part. So when would 2/3 of x have a magnitude less than 1? Well, 2/3 times 3 over 2, the reciprocal of 2/3 times by 2/3 would give you 1. So from the red, we need, from this red bit here, we need the size of x to be less than 3 over 2. And from the blue, we also need, well, we need what? Well, the binomial expansion for this one here was performed based off 1 plus 3 over 2x. So this part here needs to be less than 0, 2. So what value of x would make 3/2 less than 1? Again, we do reciprocal. So 3/2 times 2/3 would be equal to 1. Therefore, x must be less than that 2/3. So we need x also, the magnitude of x, to be less than 2/3. So what value of x satisfies both being less than 3 over 2 and less than 2/3? Well, if there's anything bigger than 2/3, we're not going to satisfy this blue inequality. So to satisfy both, we need the size of x to be less than 2/3. Or to put it a different way, we need x to be between minus 2/3 and positive 2/3. So whichever way you write it, one of those ways, each one is equally as valid as the other. So that's enough for me. Now it's over to you to try some. So what I'm going to suggest you do is turn to page 99, exercise 4b in the Year 2 Pure Book. Try questions 1, 2, 3, and then questions 6, 7, and 8. As ever, if you get stuck, please do check the solutions at the back, and then the model solutions if you can access them. If you're still stuck, ask a neighbour. If you're still stuck, ask me, ideally in lesson. Second best, probably on an email. Third best, please even leave a comment in the comment section of this video. It's always nice to hear from you in different media. So I hope this has been useful. Again, I feel like I'm repeating myself, but I do genuinely mean it when I say thank you for listening, thank you for subscribing if you have done, and thank you for liking. So take care of yourselves, binomial expand away until you get sick of it, and I'll see you for the next lesson. So once again, take care, and it's bye from me.